A very good morning to all of you. Today we are going to discuss on alpha beta pruning. The last session we have already seen min max search algorithm, and this session we will see alpha beta pruning. The last session we have already seen the algorithm for min max search. So the problem with the min max search is that the number of game states it has to examine is exponential in the depth of the tree. So that means the min-max explores all possible game states. If the game tree depth increases, the number of nodes increases exponentially. So this makes min-max very slow for complex games. So we can say that this is good, but it is inefficient for the large, very big games. So we can't eliminate the exponent because, but it turns out we can efficiently cut it in half. So we will see. So we cannot change the exponential nature of this problem, but we can reduce the number of nodes evaluated. So this makes the algorithm much faster in practice. So we don't search smarter paths later. We stop searching useless path early. So then it is possible to compute the correct min-max decision without looking at every node in the game tree. So min-max decision is actually the best move, but we don't need to evaluate all the branches. Some branches cannot affect the final answer. So if a branch cannot give a better result, we can ignore it. So hence there is a technique by which without checking each node of the game tree, we can compute the correct min-max decision. This technique is called a pruning. So we can say that pruning means cutting off unnecessary branches. It saves time and computation. So just like cutting unwanted branches of a tree. In alpha beta pruning, we apply standard min-max. It returns the same move as min-max would, but prunes away branches that cannot possibly influence the final decision. So alpha beta pruning is not a new algorithm. It is an optimization of min-max, and it uses same min-max logic and gives same final move, but it skips unnecessary branches or unnecessary part of the tree. So alpha beta pruning improves efficiency without affecting the correctness of the decision. So we can say that alpha beta pruning speed up min-max by eliminating branches that cannot change the final decision. So alpha beta pruning that involves two threshold parameters alpha and beta. So that's why it is called alpha beta pruning. Alpha beta pruning uses two threshold values that decide whether to continue expanding a node or uh, stop searching further. And the threshold means a limit beyond which we do not continue searching. And here we will see that two threshold values. First one is alpha, that is the best highest value choice we have found so far at any point along the path of the maximizer, and its initial value is minus infinity. Next threshold value is beta, that is the best lowest choice value that we have found so far at any point along the path of the minimizer, and its initial value is plus infinity. So here we can say that alpha is associated with the max player, and it stores the maximum value max can guarantee so far, and its initial value is minus infinity. So before searching starts, the max has no information. So the best guaranteed value is assumed to be negative infinity. And max start with the worst possible value and improves alpha as it found better course. Then next threshold value, that is beta. Beta is the lowest value choice we have found so far at any point along with the path of the minimizer. So that means beta is associated with the min player, and it stores the minimum value min can force so far. So here min will not allow the value to go above this. The initial value of beta is plus infinity. Initially, min has no constraint. So the worst case minimum is assumed as positive infinity. And min starts with the highest possible value and reduces beta as it finds worst outcomes. So the alpha beta pruning search, this alpha beta search updates the value of alpha and beta as it goes along and prunes the remaining branches at the node. So we here at the search proceeds, alpha is updated at the max nodes and beta is updated at the min nodes. So these updated values are passed down the tree. So that is very important. That means if max find a value which is less than or equal to beta, or min find a value greater than or equal to alpha, then continuing the search is useless. So max node always compare with the beta node and min node always compare with the alpha node. So alpha is greater than beta, then it will prove. We will see in detail. We can see the algorithm here. Here we can see that there is a main function, that is alpha beta search. This is the function, and the input is current game state is the input, and it returns a best action for the max player. And here we can see a max value. This actually search start from a maximum max node. So initially alpha is equal to minus infinity. That means max has no best value yet. And beta is equal to plus infinity. That means min has no restriction yet. So this max value computes the best achievable utility. And then you can see here it return an actions. So from all possible actions, choose the action that gives the maximum utility value B. And this is exactly like min-max, only it is faster. Then you can see this, there is a function called a max value function. So that is called at a max player's turn, and max tries to maximize the utility value. So if the game has ended, you can see that here terminal state. If the game has ended, that means been lost or draw. So that it returns the utility value directly. Then you are setting V is equal to minus infinity. So max starts with the worst possible value. It will try to improve V. And here you can see that for each A in action state. So max explores all possible actions and each action leads to a new game state. So after the max makes a move, min will respond, so called a mean value. So that is called a mean value, and here you can see mean value. Then the max chooses the maximum among the return values. And then we will see if V is greater than or is equal to beta. So min already has a better or lower option. So max cannot force a better result here. So this branch is pruned. So this branch cannot influence the final result. Then alpha means max of alpha comma V. So update the alpha with the best value found so far, and alpha represents max guaranteed score. And then return B. So after checking the valid branches, return the best value for max. Then you can see another function, min underscore value function. So this is called a means player turn, and min tries to minimize the utility value. And here you can see if it's a terminal node, if the game ends, then return the utility value. And here we are setting V is equal to plus infinity. Min starts the highest possible value and tries to reduce it. For each A in actions, then that means min checks all possible actions. And after min's move, max will respond and min select the minimum value. So here V is less than or alpha, then return V. So that means max already has a better guaranteed value. Min cannot make things worse for max here. Then this branch is pruned. And then we have to update beta with the still lowest value, and also that is min of beta comma v. Then beta represents means guaranteed limit and return the best solution for mean. So this algorithm is same as that of the minimax algorithm, except for the two lines in which mean value and max value that maintain alpha and beta. So the logic of min max is unchanged. Only the difference is tracking of alpha and beta and adding pruning conditions. And the result will be same optimal move and fewer nodes exploded in this case alpha beta pruning. We can see an example of alpha beta pruning. So we will start with a tree. Here you can see we have already seen this figure when we are explaining min-max. Here we can see that we have a root node, that is A. A is the max node and A has three children B, C, D. They are min nodes. So the leaf nodes that here you can see the utility values. So the max at the root chooses the maximum of its children. And each node B, C and D is a min node. So it will take the minimum of each subtree. So here we can see at the node B, there are three children, 3, 12 and 8. It will select, this is the min node. So it will select the minimum of 3, 12 and 8. Here you can see the equation, minimum of 3, 12 and 8. Then at node C, it will take the minimum of 2, 4 and 6. Here we are considering, we don't know the value of 4 and 6. We are considering it as y. So the equation will be minimum of 2xy. Then you can see at node D, the values are 14, 15, 2 are the child nodes. So it will take the minimum of 14, 5 and 2. So here we can see here minimum of 3, 12 and 8, the answer is 3. And then minimum of 2 xy we don't know, it will be depending upon the value of x and y. So we are writing like this, minimum of 2xy. Then minimum of 14, 5, 2, it will be 2. The minimum value is 2. So the equation is modified like this. So we will get the value. Here it is 2, 3 and here we don't know. So here it is minimum of 2xy and at node D the value is 2. So here this minimum of 2 comma xy means this will be anyway it will be less than or equal to 2. If whatever will be the value of x and y, it's taking the minimum value, right? Then the value, there is a 2 is there. So it will take, anyway, it will take a value which is 2 or less than 2. If the x value is greater than 2, we will not consider. If y value is greater than 2, we will not consider. If it is less than 2 only, we will consider. So we can say that it can be 2 or less than 2. And now we are coming to the max node. It will take the maximum value. So it will take 3, then we don't know this value, then 2. So it will take the maximum of that. So maximum means anyway this part minimum of 2 comma x comma y, that will be 2 or less than 2. So we know that 3 is greater than that. So we will always take 3. So the maximum of 3 comma minimum of 2xy comma 2, we are considering it as 3. So here the answer is 3. So we can say that the value of the root and hence the is 3 and hence the min max decision are independent of the values of the pruned list x and y. So no matter what values x and y will take, they cannot change the final decision. So these nodes are pruned. So here we can understand that if we are not considering these two nodes also, we are getting the final decision correctly. Now we will be explained the step by step of the diagram. Here we have A is the root node. Here alpha and beta have the initial value. Minus alpha is equal to minus infinity and beta is equal to plus infinity. Here we know that my node A is actually the max node. So it will select the maximum value and its child node B, C, D are the min nodes. So that will choose the minimum value. So the max node it will update the alpha value and min node it will update the beta value. So initially alpha is equal to minus infinity, beta is equal to plus infinity. That will be propagated downwards. At node B, this is the min node. So it will consider it's a leaf nodes. So first leaf node has the value 3 and 3 and this beta value will be compared and we will choose the minimum value. So plus infinity and 3, which one is minimum? 3 is minimum. So here beta is updated to 3. Next, you can see the next child leaf node of B is 12. And when we are comparing 12 and 3, still 3 is the minimum. So there is no change. So the value of B is still at most 3. Then the third leaf node of B is 8. Here you can see that its value is 8. And we have seen all B successors. So the value of B is exactly 3 itself. So now we can infer the value of the root is at least 3 because here this here B is a min node. So it will choose the minimum value of the utility values of the leaf node. So 3, 12 and 8. So here the utility value will be 3. Then next we will see the we will see the leaf nodes of C. C is also a min node. So here it will also update beta. So initially beta is plus infinity. It will compare with its leaf node that is 2. So 2 and plus infinity will be compared. So it will be updated to 2 because 2 is the lowest value. So but we know that B is worth 3. So the max would never choose C because here this A is the max node that will take the maximum of its childhoods. So here B the value is 3 and whatever will be the value here if it is 2 or less than 2 it will take 3 only. So and this C will select the minimum of its child node values. So it will be anyway it will be 2 or less than 3. So there is no need to check the remaining leaf nodes. So there is no point in looking at the other successors of C. So this is the example of alpha beta pruning. Now we are moving to the node D. So node D is also a min node. So it will update beta. So it's a first leaf node is value is 14 and so 14 and plus infinity will be compared. So 14 is less and here D is worth at most 40. So this is still higher than max best alternate. That is it is higher than 3. So we need to keep exploring these successors because if the value if we have a value less than 14 it will be updated. So we have to check the successors of t. So here you can see that the next node is utility value is 5. 5 and 14 will be compared, which one is less for 5, so it will be updated as 5. The next leaf node is 2 and 2 and 5 will be compared. So the less value is 2. So it will be 2 only. So here the utility values of B will be here it is 3, here it is 2 and here it is again 2. Here value is 2. And so then we have the max node that is A. A will select the maximum of these 3 comma 2 comma 2 maximum of this will be selected. So that is 3. So so here we can prove this successors of C here. That is we explained in detail with another example. The explanation is given here. So the condition of alpha beta pruning. The main condition required for alpha beta pruning is alpha is greater than or equal to beta. So this is the condition. So alpha represents the best value, that is max can guarantee so far, and beta represents the best value min can guarantee so far. When alpha becomes greater than or equal to beta, then further exploration cannot improve the final decision. So the remaining branches are pruned. So once alpha is greater than or equal to beta, continuing the search is useless. Then we will see some key points. The max player will only update the value of alpha. max is trying to maximize the utility value, so it only updates alpha. So alpha will be maximum of current alpha value, and then the next level alpha value we will compare. So max never updates beta. Next, min player will only update the value of beta. So min is trying to minimize the utility value, so it only updates beta. So min will never update alpha. Then next point, while backtracking the tree, the node values will be passed to upper nodes instead of value of alpha and beta. So that means after evaluating a node, the computed min-max value of the node is returned. Alpha and beta value are only control values, not the final results. So the parent node use the node value, not the values of alpha and beta. Alpha and beta gate pruning, not the final utility value. Then we will only pass the alpha and beta values to the child nodes. So during recursive calls, current alpha and beta bounds are values are passed downwards. So this allows child nodes to decide early whether the pruning is possible or not. So alpha and beta flow downwards, and the the node values that will be flow upwards. Let us take an example of a two-player search tree to understand the working of a alpha beta pruning. So we can see the figure here. So before starting that, we have to remember max player wants the highest value and min player wants the lowest value. And we will get we still get the same final answer as the min max. So, but we avoid exploring useless patterns. So if you already found a better option, there is no need to waste time for checking the first ones. So here uh, we will start with the two threshold values, alpha and beta. Alpha means the best value max can guarantee so far, and beta is the best value mean can guarantee so far. And if alpha is greater than or equal to beta, then we will stop exploring that branch, or that is called pruning. So we will start from the root node. Here root node is A, and the starting value of alpha is minus infinity and beta is plus infinity. And max explores the left subtree first. So we are moving to B. And then B value is still alpha is equal to minus infinity and beta is equal to, here it's a, here again alpha is equal to minus infinity and beta will be equal to plus infinity. This will be plus infinity. So that means alpha and beta that propagate downwards. So then go to beta nodes. So here beta, and again alpha is equal to minus infinity and beta is equal to plus infinity. And here we know that this A is the max node, B and C are the min nodes, and D, E, F, G are the max node, and these are the terminal values. Then we will see at node D what it will happen. So at a node D, the value of this is the max node. D is the max node. So the value of the alpha will be updated. So alpha will be calculated. Here we can see that D has terminal nodes 2 and 3. It will select the maximum. This is the max node. So it will select the maximum of 2 and 3. So value is 3. 3 is the maximum value. So its min max value is 3, and also it updated alpha. Alpha, if initial value is minus infinity, it will compare minus infinity and maximum value of 2 and 3, that is 3. So then 3 will be the maximum. 3 is greater than minus infinity, so alpha will be updated. So here alpha is equal to 3 and beta there is no change. Max not will update only alpha, and the min max value is 3. And this min max value will propagate upwards. So, here this is the min node. So it will compare with the beta value. So here beta value is it was plus infinity. So it will check whether plus infinity or 3, which one is less. So here 3 is less. So beta value is updated here. You can see minimum of plus infinity and 3, because we know that initial value of beta is plus infinity. So it is propagated downwards. So at node B, initial value is beta is plus infinity. So we will check plus infinity or the min max value. Min max value propagate upwards. So 3 and plus infinity, which one is less? Min node will select the minimum value. So 3 will be selected. So beta is updated as 3. Now, in the next step, algorithm travels the next successor of node B. That is, here we can see E. So, we already discussed alpha and beta value will be propagates downwards. So, here alpha is equal to minus infinity, beta is equal to 3. That will be propagate downwards. So, to node E. And node E actually choose first leaf node is 5. So 5, and here this is the max node. So will alpha will be updated. So alpha is minus infinity. Initially it is minus infinity. So minus infinity or 5. Which one is higher? 5 is higher. So it will be alpha will be 5. And then 5, and so here you can see alpha, whenever alpha value is greater than or equal to 3. Now you can see when alpha is equal to 5, beta is equal to 3, then that means that here alpha is greater than beta, then we will not we will not we will not go forward. So we are pruning that path. So here we know that here we are not considering 9. So here the 9 max value is 5. So the 5 will be upwards. So here 3 and 5 will be compared here. This is min naught at B, min naught. So here it is 3 value, here it is 5. So minimum value will be selected. So here min max value is 3. Then so next step, the algorithm again backtrack the tree from node B to node A. So here you can see that here alpha is equal to minus infinity and beta is equal to plus infinity. And here this is the max node. So that means it will update the alpha. Here the min max value will be 3. So this will be compared with the alpha value. Here alpha is equal to minus infinity and 3, this 3 will be compared. Which one is maximum, that will be selected. So 3 is maximum. So alpha is updated to 3. And this alpha and beta value will be propagated downwards. So it will here C also alpha is equal to 3, beta is equal to plus infinity. Again it will be propagated downwards. Alpha is equal to 3 and beta is equal to plus infinity. Here F has two leaf nodes 0 and 1. So first it will compare 0. Here this is the F is the max node. So it will update alpha. So 3 and 0 will be compared. Which one is maximum? 3. So there is no change in alpha. And again next leaf node 1. 1 and 3 will be compared. Again maximum is 3. So there is no change in alpha. But the min max value will be changed. Min max value will be maximum of 0 and 1. That is 1. And this 1 will be going upwards. Next, you can see here. Here at C, there is alpha is equal to 3 and beta is equal to plus infinity. And this here, this is the min naught. So beta will be compared. So beta is equal to plus infinity, and here the min max value is 1, that will be compared, and which one is the minimum. So plus infinity and 1 is compared and minimum is 1. So we are updated to beta is equal to 1. So but now there is a condition, alpha is greater than or equal to beta. Here alpha is greater than beta. So that means in here, so the next child node of C, that is G, will be proved. So the algorithm will not compute the entire subtree G. So it will not compare this part. So we are not exploring this part. And this already we have proven this part. And now, so here the min max value will be 1, because here we have only one value. Next last step, now C now returns the value 1 to A, and this is the A is the max node, and there are two min values 3 and 1, and this max value will select the maximum value, maximum of 3 comma 1. So 3 will be selected. So following is the final game tree, which is the showing the nodes which are computed, and nodes have never computed. Hence, the optimal value of the maximizer is 3, and this is the path A to B, B to D, B to O, then D to this 3. So this is the. Then next is move ordering in alpha beta pruning. So in this example, what we have done is we are starting exploring the child nodes. We are always starting from the left side. So is the order matters. So so we know that alpha beta pruning is powerful only if we look at good moves early. So the earlier we find a strong move, the more branches we can safely skip. So here move ordering means the sequence in which child nodes are evaluated in the game tree. So alpha beta actually uses DFS from left to right. The nodes examined earlier strongly affect the pruning. So nodes examined later may never be visited. So alpha beta pruning works by alpha by two thresholds, alpha and beta. We already know that. And if the good moves come early, then alpha increases fast, and beta decreases fast. So that means alpha is greater than beta will happen earlier, and we can get more pruning. And the worst ordering means best move is examined last. So alpha and beta update very slowly, and no pruning happened there. So algorithm behaves like a normal min-max algorithm. There the time complexity will be big O of b to the power m. Alpha beta does extra work but um, get no benefit actually. But if we have the ideal ordering means best move is examined first, alpha and beta get strong values earlier, and large part of the tree are pruned, and many nodes are never evaluated. So in this case, we can reduce the time complexity as big O of b to the power m by 2. So half the depth explored, we are exploring only the half the depth. So we can increase the speed. So most commonly we are first exploring the left side. So if we have good moves in the left side, we will get high pruning, and uh, right side bad moves means no pruning. So since DFS goes left side, put best moves on the left. That is the ideal ordering. Put best moves on the right means worst ordering. Now we can see an example for alpha beta pruning. So here in this example, here A is the root node and A has two child nodes B and C, and then B and C has child nodes D, E, F, G. We can see that root node we are marked it as max node, and next child nodes we are marked it as min nodes, and next level child nodes we are marked it as max nodes. Alternate levels we are marking it as max and min. So here always start with the max at the root node. So here we are starting at a root node A. So here A we are marking it as here you can see that at A we are taking alpha is equal to that is our initial condition minus infinity, and beta is equal to plus infinity. This is always our initial condition at a root node, and this alpha and beta value will be propagated downwards. So here at B also we have alpha is equal to minus infinity and beta is equal to plus infinity. So alpha and beta value will be always propagate downwards. And again at D also alpha is equal to minus infinity and beta is equal to plus infinity. So here we know that at node D is a max node. So it will select the maximum value. So it will update alpha. The max node will always update alpha. It will not update beta. So what it will do? It will compare the leaf node value with the alpha. So it will check whether 3 or minus alpha, which one is maximum, because this is the max node. So it will check whether the 3 or minus infinity, which one is maximum. 3 or minus infinity, which one is maximum. So we know that 3 is maximum. So what we will do, we will update alpha as 3. Then it will compare with the next value 5. So 5 or 3, we are D is a max not, so we will update only the alpha value, we will not update beta value. So 5 or 3, which one is large? So here 5 is large, so again we are updating alpha as 5. So now alpha is equal to 5 and beta is equal to plus infinity at node T. And we will choose the min-max value. Min-max value, this is a max node. So it will select the maximum value from the leaf node value 3 or 5. Which one is the largest? 5 is the largest. So min-max value is 5. And this min-max value will be propagate upwards. So alpha and beta value will never propagate upwards. It will only go downwards. And the min-max value will go upwards. So here B is a min node. So min node means that means it will update beta. It will not update alpha. So beta value is plus infinity. So it will compare plus infinity and the min max value, that is 5. So 5 or plus infinity. Which one is minimum? 5 is minimum. So it will update instead of 5 plus infinity, it will become 5. And this alpha beta value will be go downwards. So it will go downwards, that at not E, then alpha is equal to minus infinity and beta is equal to 5. And here you can see this E is a max node. We know that this is a max node. So it will update alpha only. So this will compare the leaf node value 6 with the minus infinity. 6 or minus infinity. This is a max node. So it will select the maximum value. So which is maximum? 6. So it will update it to alpha is equal to 6. Now the condition is satisfied. Alpha is greater than, here alpha is greater than beta. So it will not consider the further node. So it will not explore the next leaf node. So here the min max value will be 6 because we are not exploring the next node. So there is no need to consider that. Here we have only one value, that is 6. So 6 will go upwards. So it will at B node, it will compare 5 and 6. Which one is? 5 is the min max value of D and 6 is the min max value of E. So which one is the in the case of D, it's a min node. So it will choose the minimum value. So it will choose 5. It will choose 5 only. Then this 5 is going upwards. So this 5 is going upwards. Here 5, min max value is 5 and 5 is going upwards. So here A is a max node. So it will update always alpha. So alpha and 5 will be compared. So alpha and 5 will be compared. Which one is maximum? 5 is maximum. So it is updated to 5. So this alpha and beta value go downwards. So here alpha is equal to 5 and beta is equal to plus infinity. So again it is going downwards. Alpha is equal to 5 and beta is equal to plus infinity. Now we have the leaf node 1. So here F is a max node. So it will update only alpha. So alpha value 5 or 1. Which one is the large? It is a max node. So it will select the maximum value. So 5 is maximum. So it will not update. Then again next node 2. So 2 or 5. Which one is higher? 5 is higher. So it will not update the alpha value. And here the min max value will be 1 or 2. Which one is the largest? 2. So here min max value is 2 and it will go upwards. And at node C, that is a min node. So it will update beta. So it will check minus infinity or 2. Minus infinity or sorry, this is plus infinity. This is plus infinity. The beta value here at node A, it is plus infinity. So plus infinity is going downwards. Here alpha is equal to 5 and beta is equal to plus infinity. So here this 2 is compared with the plus infinity. So which one is minimum? 2 is minimum. So we are updating it as 2. Then here 5 or 2. So here you can see alpha is greater than beta. So the successor of C will be, that means that subtree will be pruned. So we will not consider all these nodes. So here we can see that we will not consider this right path. here we have only 2 is the min max value. So at node C also the min max value will be 2. So here it is 2 and B has 5. So A is the max node, it will select the maximum value. So maximum value means it will select 5 or 2. The min max value 5 is the maximum. This is the max node, it will select the maximum. So 5 is the min max value. And if we are checking the alpha value is compared with the 2, 5 or 2, which one is higher? 5 is higher, so it will not update. So here our final solution path will be, here you can see that from A to B to D to 5. So this is the final path. And the min max value will be 5. So the same figure, here we can see the pruning and all, it is described here. So we will see the next example. Here we can first give the node names. Here it is A, and here we have B, then C, then D, then child nodes E, F, G, H, I, J, and K. So we know that the root node we are setting it as max, then min, then max. Alternate levels we are marking it as max and min. So here you can see alpha in our initial state, alpha is equal to minus infinity and beta is equal to plus infinity. We are always starting with this condition, initial condition, alpha is equal to minus infinity and beta is equal to plus infinity. And alpha value and beta value will go downwards. It will only go downwards. This will not go upwards. So alpha is equal to minus infinity and beta is equal to plus infinity. So at node E, we are comparing with leaf node. So we know that E is a max node. So it will compare alpha and the leaf node value. So here what it will do, it will find maximum because this is a maximum node. So it will select maximum of minus infinity and the leaf node value 4. Which one is largest? 4 is largest. So it will update 4. Alpha is equal to 4. At node E, this is a max node. So it will update only alpha. It will not update beta. Next, it will compare with 3. 3 or 4, which one is maximum? Next, it will compare max of 4, comma 3. So, which is the largest? 4 is the largest, so there is no change. Then we have to find the min max value of E. Min max value of E will be, this is a max node, so we have to find maximum of 4 and 3, that is 4. So, this node value will be 4. And this node value will go, this node value will go upwards. So at node B is a min node, so it will update beta. So it will compare beta and 4. So what it will do, it will find minimum of, because this is a min node, it will find minimum of plus infinity, that is the beta value, and the min max node, that is the min max value is 4. Which one is minimum? So if 4 is minimum, so it will update it to 4. So now the beta at node B, alpha value is minus infinity and beta value will be 4. So it will go downwards. So at F, we can see alpha is equal to minus infinity and beta is equal to 4. Now we will compare with the leaf nodes. F is a max node, so it will update alpha. So it will check whether maximum of minus infinity, that is alpha value is minus infinity and 6. Which one is maximum? 6 is maximum. So it will update it as 6. So alpha will become 6. So now the condition is satisfied, that is alpha is greater than beta. So it will not check the successors. So it will not consider the next leaf node. So here it will consider only 6. Here this is pruned. This path is pruned. So the min max value will become 6. So this 6 is going upwards. So B is a min node. So here beta value will be compared. So beta value means this is min value. Min value of beta value is actually 4 and the min max value compared is 6. So which one is minimum? 4. So it will this 6 will be compared. So there is no change. Then
you can see here F has value 4 and E has value, F has value 6 and E has value 4. And when we are comparing these two at node B, the min-max value will be 4 because we select the minimum value 4 and 6. 4 and 6, 4 is minimum. So this 4 go upwards. And at node A, the alpha value will be updated. Alpha is maximum. Alpha is maximum of minus infinity and 4. What is the maximum? 4. So it is updated to 4. Then this go downwards. You can see at C alpha is equal to 4 and beta is equal to plus infinity. Then it will go downwards. Alpha is equal to 4 and beta is equal to plus infinity. Then at here you can see here the leaf node is 2. So here G is a max node. So alpha value will be updated. 2 and 4 will be compared. 4 is the largest, so there is no change. Then 1 and 4 will be compared. So there also 4 is the largest, so there is no change. But the min-max value when we compare 2 and 1, which one is the largest? 2. So this 2 go upwards at C. So C you can see here this is the min node, so beta will be updated. So beta is plus infinity or 2. Which one is the minimum? 2. So it will be updated to 2. So here alpha is greater than beta. So the successors of C will be pruned. You can see we will not explore H and I. That is pruned here. All these parts are pruned here. So then you can see here, here at node C, the min-max value will be 2 because we have only this value. Remaining all child nodes are pruned. So 2 will go upwards and it will compare with the alpha value. Alpha value is actually 4 and 4 and 2 compared. Which one is maximum? 4 itself. So there is no change. Then alpha beta value will be go downwards. So here at node D, alpha is equal to 4 and beta is equal to plus infinity. And then at node J, alpha is equal to 4 and beta is equal to plus infinity. And here you can see we are comparing with the 5 and 4. So it is J is a max node. So alpha will be updated. 5 or 4. Which one is higher? 5. So it is updated. Then 4 or 5, 5 is the highest value. So alpha is equal to 5, beta is equal to plus infinity. And when this comparing this, what is the min max value of J? Min max value of J is maximum. So it will be 5 itself. Then you can see so this 5 go upwards and at D beta is updated. This is a min node, so beta is updated. So plus infinity or 5, which one is minimum? 5 is minimum, so it is updated to 5. So here beta will be 5 and then you can see here this alpha is equal to 4 and beta is equal to 5 will be go downwards. Here you can see this is a max node, so alpha will be updated at K. So 7 and 4 will be compared. It is 7. So now alpha is greater than beta condition is satisfied. So this is pruned. It will not check the next leaf node. So here the min max value will be 7 only, and here it is 7 and this is 5. So which at node D, what will be the min max value? Here this is a min node. So here 5 or 7, which one is the minimum value? 5 is minimum. So here the min max value is 5 and this 5 goes upwards. Here 5 and here it is 4. You can see at B 4, C it is 2 and at D it is 5. So which one is the less value? Which one is the maximum value? That is 5. So here at node A, the min max value is 5. And this 5 value is compared with the 4 here, alpha value 4. So alpha value 4, which one is the highest? 5 is the highest. So alpha is updated to 5. So here we can see the solution. Now we can see the solution. So all the nodes having min max value 5 will be selected. So here you can see here this is the path. We have 5 as the min max value. So this is the solution of this problem. So the pruning is also shown in the figure. You can see this is pruned and this path is pruned. All these paths we are not exploring because their alpha is greater than beta. That condition is satisfied. So this is example for alpha beta pruning, and in exam we will ask we can have a short question alpha beta pruning for using alpha beta pruning. Thank you.